Hello. I guess it is working now. Um, I can see only three people have joined. Can some of you just confirm if the microphone is working and you're able to listen to me? I'll just allow one of your mics. Divya, I have allowed your mic. Can you confirm if you can hear me?
Um, yes, I can hear you.
Okay, thank you. All right, sorry, we'll wait for some more time so that we'll allow other people to join and then we'll start the session.
Okay, sir.
Yeah. Yeah. Yes, you're allowed to keep your cameras open, your videos on. However, for the sake of convenience in conducting this meeting, we have disallowed your mics, your microphones. So as and when required, and if you want to ask something or respond to some of the questions, then you can raise your hands and using the meeting option, and then I'll allow your mic and we can discuss. Is my screen visible?
Yes, sir.
And is it changing when I'm changing the slides too?
Yes, sir.
Okay. It's around 6:11 now. We'll start the session at 6:15. All right, let's start the session. Hello, everyone. Welcome to the second weekly discussion and doubt clearing session of the NPTEL course on concrete technology, NOC24-CE46, which is taken by Professor B. Bhattacharya of IIT Delhi. I am Ashirbad Satpathy. I'm a PMRF research scholar at IIT Delhi, and I'm also the officially assigned teaching assistant for this NPTEL course. What I do is I take these weekly sessions where we discuss several practice problems related to this NPTEL course, and also we take the doubts that you might be having regarding the previous week's lectures. There is another teaching assistant to this course. His name is Debojyoti. He also takes these weekly discussion sessions, and he usually takes his sessions on Saturdays from 6 to 8 p.m., while I take my sessions on Mondays from 6 to 8 p.m. Besides this, the week one discussion session has been uploaded on YouTube, and I have shared the link of the same in the chat section. Also, the lecture slides that we use during these sessions, that has also been uploaded on OneDrive, and the links have been shared on the chat section of this meeting. In today's session, we'll be discussing several practice questions related to week 2 lectures. In this week 2 lectures, you were taught about the various types of cements and their uses and in particular applications, how cement hydrates, how porosity is embedded when cement gets hydrated, and then you discussed about the several tests related to the physical and chemical parameters of cements. Then we discussed the different types of aggregates and the properties of aggregates and how they influence the properties of concrete later on. So yeah, we'll be taking certain practice questions related to these week 2 lectures, and then at the end, we'll also clear the doubts that you might be having regarding the week 2 lectures. So the first question is, the volume before and after hydration is conserved. You saw that in the lectures also. While calculating the porosity of cement, hydrated cement, we conserved the volume, as you can also see in this picture as well. What is the assumption here? What is the assumption that we are doing when we are conserving the volume before and after the hydration? Yes, anyone would like to attempt to this question? You can raise your hands and I'll allow your mic and you can answer. Yes, yes, Divya, go ahead.
Yeah, assuming that no water is lost during evaporation.
Okay, yeah, no evaporation has taken place and the water hasn't dried out instead of getting hydrated. Okay, that is one of the assumptions. What else? So if the water doesn't get evaporated, if it gets evaporated, then what will happen to the volume?
The volume of water available for hydration will reduce.
Okay, what will
So there will be
happen?
less water in the gel pores or less capillary water.
Okay, right. What will happen to the total volume? It will reduce, right?
Will
Yeah,
reduce.
yeah. What do we call when there is a reduction in the volume? What do we call it in cement chemistry terms? Or any mechanical terms per se? Yes, you want to try? Okay, thank you, Divya. Anybody else wants to try this? Try answering this question. Okay. One was answered by Divya. It is water hasn't evaporated. We are assuming that. And that is basically, so when there is a change in volume, we call it in mechanical terms, we call it, or not a change, rather a reduction in volume. Reduction in volume is called shrinkage, while increase in the volume is called expansion, right? So this is the word I was looking for, shrinkage. So we are assuming that there is no shrinkage occurring when we are doing volume conservation while calculating the while talking about the before hydration and after hydration state of cement. So there are several types of shrinkage that cement can undergo during and after it, I mean during its hydration process. And this starts with, first is called chemical shrinkage. So I'll just briefly discuss all these types of shrinkage that we have totally assumed while we are conserving the volume. And I'll just briefly discuss these different types of shrinkage, because these might also be discussed in later on in the course as well. Or I don't know, but yeah, it might so happen. So first is a chemical shrinkage. What is chemical shrinkage? Does anybody wants to answer? Okay. Chemical shrinkage is when the cement is still in its plastic stage. So when the cement is still in plastic stage, the initial chemical shrinkage is the reduction in volume due to the formation of early hydration products. So as we know, the volume of early hydration products is lower than unhydrated cement plus water. So this part is due to this. It is chemical shrinkage because the volume of hydration products is lesser than the total volume of the unhydrated cement plus water, right? Now there could be bleeding. Let's say there is certain amount of segregation. This is for the first type of shrinkage, the chemical shrinkage. Then there could be bleeding in the mix as well. Let's say your aggregates, there is a segregation in the mix. Segregation is settling down of the heavier particles while the lighter matter comes on the top. So your aggregates are trying to settle down, and the bleed water gets accumulated on the top, forming a film. And when this film is formed, so initially the volume was this much. Initially the volume was, when you cast a cube or something, initially the volume was the same, right? And this was a homogeneous, more or less homogeneous mix. But with time and due to segregation, the heavier particles have settled down, while the bleed water has accumulated in the bottom, and therefore this difference in volume is called as subsidence. That is, the cement or the concrete has now subsided or acquired a lower volume, while the top portion of it has been accumulated with water. So this is known as subsidence, as it is mentioned over here. So this is the total of this. This is the first one. Then, while it's just starting to set, this is the second one, subsidence. When the um, when the cement or the concrete is just starting to set, then there could be autogenous shrinkage. And autogenous shrinkage is also known as self-desiccation. It is basically, so autogenous shrinkage after the setting is known as self-desiccation. this is when there is already a rigid framework of the hydration products, because it is already set. So there is already a rigid framework of the hydration products, and now that the cement is still undergoing hydration, so it is taking the water from the capillary pores. So since it is taking the water from the capillary pores, there is a suction process going on, and therefore there's a shrinkage in the volume. So this is also due to the chemical reactions that are going inside the concrete or the cement, but after the cement has set. So uh, this autogenous shrinkage is after, I mean, the autogenous shrinkage that undergoes after the setting is very little in amount, and therefore, as you can see in this view graph, the chemical shrinkage is much higher. The total chemical shrinkage is much higher than the autogenous shrinkage, right? Because the chemical shrinkage is the shrinkage when the cement or the concrete is still in the plastic state, it is able to flow. So if there is a volume change, it can undergo that. But after it has set, the autogenous shrinkage is due to the chemical reaction still going on after the cement and concrete has set, and therefore it can't undergo as much volumetric reduction as it should have undergone if it was in a plastic state. So the autogenous shrinkage is less in amount. All right. So these are the type of uh, different types of shrinkage that it undergoes within a few hours to 1 or 2 days of the setting, right? And now we are going to look at other types of shrinkage that can occur till years after the casting. The first one is a plastic shrinkage, which is basically drying of water when concrete is still plastic, right? It occurs within the first few hours of the casting or after the addition of water. Then comes thermal shrinkage. What is thermal shrinkage? Can anybody answer? Okay. Thermal shrinkage is basically when the concrete is when water is initially added to the concrete, the chemical reactions undergo the dissolution and precipitation undergo at a very high rate, and therefore the heat of hydration at initial stage the heat of hydration is quite high, hence temperature is high inside the concrete, right? But with time the temperature reduces. Now why, when the temperature is high, the volume is higher because the volume expands when the temperature increases. But when the temperature is reduced, the concrete has cooled down, and it has been several days after the casting. Um, Now that the concrete has cooled down, so the expanded volume wants to contract. So there is a shrinkage. And since it has been several days after the casting, so the concrete has hardened. And now that it wants to undergo a shrinkage, there might be cracking in the hardened concrete due to thermal shrinkage. Plastic shrinkage also undergoes certain kinds of cracks. You can see it when this when you have cast a small sample or a cube or some kind of a specimen, and you can see that if you have left it open without sealing it, if you have left it open to interact with the environment, you can see that certain amount of I mean certain map cracks are visible on the top surface of the cast sample, and this is basically due to the combined action of chemical shrinkage, autogenous shrinkage, and the plastic shrinkage, majorly due to the plastic shrinkage, because the water on top is getting evaporated, so the top layer is trying to shrink, and therefore it is undergoing small cracks on the surface. And then, as we discussed, autogenous shrinkage, it can start from the fresh state, and the autogenous shrinkage after set can undergo till several months. And then there is drying shrinkage. Drying shrinkage is again loss of water due to drying after the concrete has hardened. Again, this also will induce cracking in the concrete. And then the final one is carbonation shrinkage, and this occurs generally after several years, and this is due to carbon dioxide present in atmosphere. When this carbon dioxide reacts with the concrete, it produces calcium carbonate, which is denser than the hydration products, and therefore carbonation induces a shrinkage. Because it is denser, so it will occupy a lower volume, and therefore the cement or the concrete undergoes a certain amount of shrinkage. And this view graph shows you the intensity of the shrinkage in very crude terms, or the degree of shrinkage in the amount of change in the volume, in the relative amount of change in volume, versus the time at which these kinds of shrinkages take place. This view graph has been taken from another course of NPTEL, which is the Durability and Repair of Concrete Structures, taken by Professor Radhakrishna G. Pillai of IIT Madras. All right. So that answers our first question briefly. So we discussed all the different types of shrinkage, and since shrinkage is not considered, therefore we are able to conserve the volume before and after hydration. Moving on to the second question, what is the standard consistency of cement paste? It is the water at which of these options are correct, you have to pick. So what is the standard consistency of cement paste? It is the water at which optimum workability is obtained, full hydration occurs, open air voids are isolated to air bubbles, maximum strength is achieved. Which of these options is correct and why? Can somebody answer to this question? I'd request you to keep this session interactive, because there are not many people in the session anyway. So yeah, you can just try, raise your hands and I'll allow your mic, and you can just try answering these questions. Yes? What is the standard consistency of cement paste? Pavitra, Tanusha, Vivek, anybody wants to try? All right. Yes, Vivek, I'll allow your mic. Yes, Vivek, you can unmute yourself and speak.
Hello, sir.
Hello.
I think full hydration occurs.
Full hydration occurs at standard consistency. How? Why do you think so?
Sir, In standard consistency determines water content.
Okay. What water content?
Uh,
It is
it
the water.
requires
Yeah.
produce to cement paste. I think which is 30% of weight of cement.
Okay. So, do you say that at 30, so at a what 30% of weight of cement means a water to cement ratio of 0.3. Do you mean to say that at 0.3 water to cement ratio full hydration can occur?
I don't know, sir. Please
Okay.
elaborate.
All right. Okay. Thank you. Thank you for attempting. Anybody else wants to try? All right. So, the correct answer to this question is it is open air voids are isolated to air bubbles. This is also discussed in the lecture as well. It is not the full hydration. It's not about full hydration. So basically, full hydration, as you can, as you might have seen in the lectures as well, it occurs around 0.38 to 0.44 water to cement ratio. And typically, the standard consistency of OPC, ordinary Portland cement, is ranges between 26% to around 32%. So this is not about full hydration. No. So this is the wrong answer. Uh, Optimum workability is obtained. Again, workability is a very subjective term. As to workability is subjective to the kind of application that you're looking to make the concrete for. For example, if it is a slab that you're going to cast, then you would want the workability to be such that the slump would be of that of a flowable concrete, let's say around 150 to 180 slump, and you'll be able to pump the concrete because there will be a congestion of the steel reinforcement on the slab or the raft. So you want your concrete to flow on its own and occupy all the spaces so that you'll have a perfect shape of the concrete element, as well as your voids will also be reduced. There will not be any kind of honeycombing on the in the concrete element. So for a slab, you would want your workability to be such that the slump is around 150 to 200 right? But if it is a roller compacted concrete for a pavement, then you would want your slump to be zero, right? So for in that case, the zero slump concrete is a workable concrete. But will that concrete work in the case of slabs? No. A zero slump concrete in the case of slabs is considered bad. It's a less workable concrete. Yes. While if it is a flowable concrete, so we generally confuse with flowable concrete and workable concrete. Flowable is the degree of flowability or how high the slump is in very crude terms. But workability is very subjective. It is related to the kind of application that you're looking for. If it is a stiff concrete that you want to make for a pavement, then you want a stiff concrete, and therefore the stiff concrete in that case is a good workable concrete. You don't want a flowable concrete there, like for a slab, right? So that's what it is. So this is a subjective term, and often combined with the application of concrete. So optimum workability can only be defined when you're able to define the application. And standard consistency is a constant value for a given type of cement, and therefore optimum workability is not the right option. Then comes maximum strength is achieved. Strength depends on and this is the ultimate or later edge strength I'm talking about, depends on a lot of factors. One could be degree of hydration, and the major factor that governs strength is porosity, because if the voids are less inside the concrete, then the strength will be higher, and so on. So there are a lot of factors that govern the strength, and not just the standard consistency of cement paste will ensure that the maximum strength is achieved. So it is not the right answer. The right answer is open air voids are isolated to air bubbles. So it was also shown to you in the lecture as well. Let's say these are the unhydrated cement particles inside a given matrix, and this used to be the air void. Upon adding water, what happens is this void trapped between these particles is slightly filled by water, while there is still air entrapped within the voids, and it is connected. The air voids are connected. But when the cement is at its standard consistency, what happens is the connectivity of the air voids is lost. So the water takes most of its void volume, and the cements are the air voids are reduced to air bubbles. So the connectivity of air voids is lost. Now what happens when the connectivity of air voids is lost? So now that the water has surrounded the air voids, and they have turned into air bubbles, there's a lubrication layer between the air voids and between the cement solid particles as well. So now that there is a lubrication inside this lubrication water that is present within the solid particles, that is able to make the particles move around. So that provides us with a kind of consistency, and it also increases the compaction, the level of compaction inside the paste. So this is the water content. The standard consistency is the particular water content at which these air voids, the connectivity of these air voids are isolated, and they turn into air bubbles, isolated air bubbles. So this is the correct answer, right? Moving on to the third question. Fineness and specific surface area values can vary with the choice of the method of measurement. You have seen two different methods of measurement of specific surface area. One is the Wagner method, and the other one is a Blaine's apparatus method. Right? Now, the question is, which of these factors listed below affect these measurements of specific surface area and fineness? The options are: the particles are assumed spherical, higher free lime content in the material, degree of flocculation of the particles, oven drying of the sample. Which of these factors are expected to affect the measurements of fineness and specific surface area of cementitious materials? Yes? Anybody would like to answer this question? You can raise your hands and I'll allow your mic to answer. Vivek, do you want to attempt? You have raised your hand, so I have lowered your hand. Probably that is from the previous question. Anyway, Tanusha, Pavitra, Munmun, you guys want to try answering this question? You can just try, and it doesn't have to be right.
Oven drying the sample.
Oven drying the sample, okay. How will it affect? This is one of the right answers, yes. Okay. I mean, multiple answers can be correct in this question, but yeah, oven drying of the sample is one of the correct answers. Can you try and tell me how does that affect the fineness and specific surface area measurements? All right. Can you speak about the other options? The particles are assumed spherical, higher free lime content, degree of flocculation in the particle. Do these factors also affect your fineness and specific surface area measurements? All right. The correct answers to this question are the particles are assumed spherical and the degree of flocculation in the particles as well, not the free lime content. And we'll discuss all these parameters one by one, all these options one by one. The first is the particles are assumed spherical. I want to ask you this question. Do the cementitious materials have spherical particles? Let's say cement, clinker, silica fume, slag, fly ash, metacoulin, different SCMs. So, do these types of SCMs have spherical particles? Yes, only in the case of fly ash and silica fume, except for and some other ashes. Let's say volcanic ash and some other ashes. Except for these cementitious materials, all other materials majorly have irregularly shaped particles. You would have seen in the case of Wagner method or in the case of normal hydrometer method, the hydrometer method, hydrometer method of particle size distribution, it assumes that particles are spherical and is based on the Stokes law. So based on the different sizes of particles, they will settle down and remain suspended at different depths in the water column, and then from that you'll be able to calculate the particle sizes. So this assumes the calculation assumes that all the particles in the system are spherical, and this will also affect the results of fineness and specific surface area, because in most of the cases of the cementitious materials, let's say clinker, limestone, slag or gypsum, so clinker, cement, any most of the cementitious materials, or in the case of metaculin as well, they have irregularly shaped particles. So assuming them as spherical would only be an approximation and would not give us right results, accurate results. The second is degree of flocculation in the particles. So when the particles are in a flocculated state, what happens is air is entrapped in these particles, particle flocks. And now this air, if the particles are not dispersed, if not dispersed properly, if these flocks are not broken, then the particle size distribution measurement will be affected. PST measurement will overestimate the particle size, meaning that particle size distribution will be more on the higher side of sizes, even though your particles are actually smaller. So it will be measuring the whole flock as a single particle, while your particles within that flock are much smaller in size. Overestimated, right? And then the third is oven drying the sample. So in the case of, if the sample has some moisture in it, then it will this moisture will also be entrapped in the air that is entrapped within the flocks of the particles, and that will get released in these measurements, this moisture, and that might also affect depending on the specific gravity of the fluid, let's say in the hydrometer method as well, on the type of fluid that you're using to measure the particle size distribution of your cement or so on, that will also affect the measurements. So you don't want moisture to be present in the sample, and therefore oven drying is a must, requirement for preparing your sample before carrying out this fineness. So moisture also affects the PSD measurements, right? All right. Moving on to the fourth question: which factors can affect the specific gravity test of the cement using the Le Chatelier's flask? The choice of medium, kerosene or water, free moisture in the material, high C3A content in the cement, air voids in the material. Which of these answers are correct? Which of these options are correct as to which factors can affect the specific gravity test of the cement using Le Chatelier's flask? Yes, anybody wants to answer this question? The choice of the medium in which you carry out the specific gravity test, meaning that it could be water, kerosene, or something else, will that affect the specific gravity test? The free moisture that is available within the material, will that affect the specific gravity test? High C3A content in the cement, I mean the composition of your cement, will that affect the specific gravity test? And then air voids in the material, will that affect the specific gravity test? Anyone would like to answer this question? Please raise your hands. Alright, the correct answers to this question are the choice of medium, kerosene or water, free moisture in the material, and air voids in the material. It could not be related to the C3A. I mean, as There is no known correlation between C3A content and specific gravity of cement. All right. Yes, of course, the choice of medium affects it because you can't carry out specific gravity tests in water medium. It will react with the water, as you might know. So we use a medium that is inert. And excuse me. Yeah, sorry. So kerosene is inert material, inert to cement, and therefore the cement will not react, and therefore the this medium will help us carry out this test. The choice of medium affects this test. Then the free moisture in the material, as discussed in the fineness measurements as well. If there is free moisture in the material, then this moisture will get released into the kerosene, and since kerosene and water are not miscible, therefore it will affect the specific gravity. So you need to oven dry the material prior to carrying out your specific gravity test. The final one is air voids in the material. Yes, of course, when the cement is in its anhydrous test, when you take it out from a cement bag, it will have air voids within the solids. And when we put it in the Le Chatelier's flask in the kerosene, we need to remove these air voids that are entrapped within the flocks or within the solids, because that will affect the volume measurement, will contribute to the volume. If the air voids are not released, if not released, they will contribute to the volume calculations, and hence specific gravity will be affected. Specific gravity is in fact underestimated, because if there is air voids trapped within the kerosene, then there will be a higher volume change with a given amount of material. So the mass to the volume will be lower. We need to release these air voids so that we get the accurate specific gravity. So the mass to the volume will be as accurate as we know, and therefore the specific gravity will be lower if there is air voids entrapped within the system. Moving on to the fifth question, what contributes to the high early strength and rapid hardening in rapid hardening Portland cement, or RHPC? It is the high bilite content? Is it the high alite content? Is it the higher fineness or high aluminate content? Which of these options contribute to the high early strength and rapid hardening properties of RHPC? High bilite content, alite content, higher fineness, high aluminate content. Anybody wants to answer this question? Vivek, Pavitra, Munmun, Tanusha. Yes,
High
Vivek.
light and light content.
What did you say?
High light content or high light content.
So you want to say both these options are correct? High B-light and high A-light content?
Or have a confusion in Belite and Elite. Actually, C3S and C2S.
Okay, yes. So B-light is C2S. I'll make this more clearer. A-light is C3S. Aluminate is C3A. Right? Now is it clear?
C2S and C3S.
You want to say that higher B-light content and high A-light content contribute to the high early strength and rapid hardening of RHPC?
Yes.
Okay. Anybody else? Okay, thank you, Vivek. Anybody else wants to try? Okay. The correct answer is actually high elite content and higher fineness and high aluminate content, not the high B-light content. You might have seen this in the previous week's lecture as well. So I'll just draw it over here just for clarity. This was a picture of, and we also discussed this in the last session as well. This is a typical strength development, compressive strength development of pure Boggs phases. And this is time in, let's say, in a log scale, and this is 28 days, and this is 56, 90, and so on. And you would be able to see that in the pure Boggs phases as an alite, the strength development goes like this. So this is C3S. In the case of B light, the strength goes development goes a little slower initially, but it catches up with A light at the end. So this is B light. But in the case of aluminates or ferrites, the strength development is limited to like this. So you can see that at around 28 days, or in the case of early strength, the only factor that contributes to early strength is A light. A light contributes to early strength. On the other hand, B light contributes to later age strength, while aluminate does not contribute much to the strength. However, the heat of hydration of aluminate is the highest, and therefore it it increases the setting action, or reduces the setting time. So aluminate contributes to rapid hardening, meaning that it makes the concrete set early, while A-light contributes to early strength. But you'd have also seen that in the case of RHPC and in when we compare between RHPC and OPC, the A-light and the aluminate contents are almost similar to that of OPC. So what contributes to the higher early strength then, if the A-lights and aluminate contents are still higher? still comparable with that of OPC. It is the higher fineness. So the last option is higher fineness. So typically, when a cement is higher, a cement is finer, the it will have large surface area. So these large surfaces will act as sites for the hydration products to get deposited on them, and for the dissolution action will also be accelerated when the surface area is also higher. So higher fineness of cement increases the rate of dissolution of clinker phases. So higher dissolution means a higher rate of hydration, and then it also the higher fineness will also provide high surface area for the nucleation of hydration products. So therefore these three answers are the correct answers to this question, right? Moving on to the sixth question: why is low heat cement used in mass concreting applications? This question doesn't have any options, so we would like to discuss it in detail as much as we want. Why is low heat cement used in mass concreting applications? Anybody wants to try? What is low heat cement? Can anybody answer to this question? What is low heat cement? Yes, anyone? What does the name suggest to you? Low heat cement.
Reduce the thermal cracking used.
Mm, yes, I mean, you can say in a sense. So, not going towards cracking, but low heat cement is basically it releases low amount of heat. The heat of hydration, the heat
Yes,
of
sir.
hydration is low. So, since the heat of hydration is low, the amount of heat getting released while the cement gets hydrated is less, and therefore it is called low heat cement. Now, why is it used for mass concreting applications? What is mass concreting? Can anybody tell me what is mass concreting? You have seen this in the lecture as well, that in the case of mass concreting applications, we want to use low heat cement. What is mass concreting? Mass concreting is basically where the size of the
Column.
elements could be the size of the concrete elements is huge. For example,
पियर पियर जो बनता है
piers,
रिवर में.
yes, piers, I mean, large piers, dams, retaining walls, all the thick structures, thick rafts. The size of the elements are huge, right? So this is known as mass concreting applications. Now, when the total amount of pour, or mass concreting is basically when the total amount of pour is very high or in a huge amount. Now, what happens in mass concreting applications is that since the thickness of, let's say, we're considering a retaining wall and it's huge, it has a high thickness, and the thickness x is very, very high, right? When the thickness of a element is too high, what happens is when the cement is added with water, it undergoes hydration, so heat is released. Now, the heat is also released from the during hydration. The heat is also released from the surface, while there is also heat being generated in the core of this is the surface heat, and there is core heat in the core of the structural element. Now, the surface heat has a way to get dissipated into the atmosphere, right? The surface is directly in contact with the atmosphere, so this heat can get dissipated from the structure. So the surface has a relatively low temperature at the surface. On the other hand, the temperature at the core is high, right? And therefore, the core is now trying to expand, expansion in the core, while the since the surface is at a lower temperature, it is trying to contract. So this induces a thermal gradient in the structural element, and this thermal gradient can lead to cracking. So when after the structure has cooled down, the expanded core would want to contract, and that in the case of hardened concrete it won't be allowed, and that will lead to thermal cracking. So what is the solution to this? We introduce low heat cement. Solution is low heat cement. So when the heat released in the cement is very low, the thermal gradient, again it will still be present because the surface is still exposed to the atmosphere, so it will have a lower temperature, while the core will have a slightly higher temperature, but the thermal gradient won't be sufficient enough to accentuate or accelerate the cracking in the structure. So uh, therefore we want to use low heat cement. Now what is low heat cement? Basically it contains, as we mentioned, the heat of hydration is low. So heat of hydration will be low when the C3A content is low. So typically low heat cements contain low C3A content, low alite content, and high B-lite content. Because we want ultimate strength in it, so we want a later age strength. We don't want it to harden, or we don't want to it to have a high heat release in the first few hours of the pouring of concrete. So we want to keep the heat of hydration very low, so therefore we reduce the aluminate content and the alite content, while we keep the baelite content high, so that it will ensure that we'll have a high later age strength as well. So this is why we use low heat cement for mass concreting applications. Moving on to the seventh question, why does sulfate resisting cement require low C3A content? So these two um, uh, question, sixth and seventh question, are quite related to each other, meaning that the low heat cement has lower C3A content, and again the sulfate resisting cement requires a low C3A content as well, lower aluminate content. What is the answer to this question? Why does sulfate resisting cement require a low C3A content? What is sulfate resisting cement? Yes, anybody wants to try? These all have been discussed in the lectures, week 2 lectures. What is sulfate resisting cement? What does the name suggest to you? Alright, I'm allowing the microphones of everyone so that we'll see if anybody wants to answer. Mudmun, Pavitra, Tanusha. I've also allowed your mics, and Vivek, your mic is already allowed. Please try to keep this session interactive. Just try and answer the questions. It need not be correct answers, and that's why we are here to discuss your doubts and to discuss the different practice problems. These practice problems are going to help you to go through this course, to actually understand this course in a deeper way, and this will also help you answer the assignment questions as well, and your final exams for this course if you have registered for it. So yeah, try and answer these questions. Just try to attempt at least, so that we'll initiate a discussion. Yes, anyone wants to try this question? Why does sulfate resisting cement require low C3A content? All right. What is sulfate resisting cement? It is a cement that resists sulfate attack. High resistance to sulfate attack. All right. Now, what does happen? Why does sulfate resisting cement require a low C3A content? What does happen when there is a high C3A content and sulfates are induced at a later age to the concrete? What happens? Where do sulfates come from?
When we increase the C3S in concrete, then deterioration is caused.
Okay, how is the deterioration caused in the case of sulfate attack? Can you answer? What kind of deterioration occurs when there is a high C3 and there is a sulfate attack on the concrete? All right. Thank you, Vivek. Yes. So if there is a high C3A content is high, and sulfates are introduced after the concrete has hardened. After the concrete has hardened, C3A plus sulfates will give rise to the formation of ettringite. And this ettringite has a high volume. And this, when precipitated in the hardened concrete, when it precipitates in hardened concrete, it creates cracking. It induces cracking in the concrete. So ettringite is good for us. So we want ettringite to be formed in the system, but when the concrete is still flowable, it is in a plastic state. When ettringite is formed in the plastic state in concrete, which is the fresh state of concrete, ettringite formed in fresh concrete can occupy as much space as much volume as required, because the concrete is in a plastic state, so there is a high porosity, there is a high amount of voids in the concrete, and the concrete can readjust itself to the amount of volume required taken by the ettringite. But when the concrete has hardened, there is not enough porosity left for the microstructure in the microstructure, and also the matrix, the cementitious matrix has already hardened, and therefore it is not able to readjust itself when the ettringite is starts to precipitate at a later age, and therefore that will induce a volumetric expansion within the concrete or the cement. And this volumetric expansion, as you know, that cement or concrete is very weak in tension. So due to this volumetric expansion, there will be tensile forces induced within the concrete or the cement, and this will lead to cracking. So in case of sulfate resisting cement, we want to keep the C3 aluminate content low, so that even if at a later age, so even if at a later age sulfate is introduced to the system, C3A will not be available in sufficient quantities for precipitation. So if the C3 content is low in the cement itself, then even if at a later age, if sulfate is introduced into the system, there will be not enough C3A left, and the C3A already present in the system in low amounts will already be hydrated in the fresh state itself. So there will not be any unhydrated C3A left in the system in order for the precipitation to occur at a later age for the ettringite precipitation. Now, where do the sulfates generally come from? How does the sulfate attack occur? Sulfate attack sources, generally soil, mostly. So when the concrete element is to be made in contact with the soil, we want to use this kind of cement, sulfate resisting cement, so that when the concrete is in contact with soil, there will be sulfates continuously coming or getting sucked from the water that is coming from the soil inside the porous concrete, and that won't affect the microstructure because the C3A content will be low. Moving on to the eighth question, what is the difference between quick set, false set, and flash set? This is an interesting question. You might have heard about different setting phenomena in occurring in cement. These are the basic three types of setting that occurs generally in cement. What are the differences in terms of composition of the cement, or in terms of you know the relative concentration of ions in the cement or the pore solution, that leads to these different types of setting behavior: quick set, false set, and flash set? What is the difference, first of all, and what leads to these different kinds of setting behavior in cement? Yes, Vivek.
क्यूब से क्यूब सेट में सर रैपिड हार्डनिंग सीमेंट यूज
क्विक सेट में रैपिड हार्डनिंग सीमेंट, ओके, ठीक है। और क्या होता है? अच्छा, नॉर्मल ओपीसी में क्विक सेटिंग नहीं हो सकता है क्या, इफ इट इज नॉट अ रैपिड हार्डनिंग सीमेंट?
व्हेन वी यूज एक्सेलरेटर
एक्सेलरेटर, ओके, ठीक है, मान लिया। फॉल सेट एंड फ्लैश सेट? What are these types of different sets? All right. this might not have been discussed in the lecture till now, but we'll go ahead and discuss this. This is a very interesting phenomena that occurs generally in the setting of cement. So these three different types of set are related to the relative concentration, related to the relative concentrations of aluminates and sulfates in the cement. So in the view graph on the right, which is taken from the book written by Mehta and Montero, this presents five different cases. So the reactivity of C3 in the clinker and the availability of sulfate in the solution. And what are the relative, uh, I mean, relative reactivity of the C3A and the relative availability of the sulfate in the solution? Depending on that, the setting behavior is governed. So as you know that aluminates, why do we introduce sulfates to cement or clinker? Because why do we add gypsum to clinker? Because aluminates have a tendency to set very quickly. So if we don't provide enough gypsum or source of sulfates, then it will form these hydrogarnets like structures, and that will lead to a very fast setting of the cement. So therefore, we want to have sulfates in the system. Now, in the case 1, when the reactivity of the aluminate is low and the availability of sulfate is also low. So if the reactivity of aluminate is low, or if the concentration of aluminate is low and the sulfate is also low, then we will have a high open time, higher workable time, longer workable time. Or let me not write it here. So case 1, I'll write it over here. Case 1, low and low. This leads to longer workable time, because since the C3 content is itself low, so therefore the cement remains workable for longer times, let's say 2 to 4 hours, and then after that normal setting occurs. Now coming to case 2, when the amount of C3 is high and the sulfate availability is also high. So meaning that there is enough sulfate and enough C3 in the system. So therefore more ettringite will be formed. So in this case, more ettringite. This case is less ettringite, right? Because the reactivity of C3 is low and the sulfate availability is also low. So in the second case, there will be more ettringite formed, high and high, more ettringite. Normal setting occurs, but it is a little faster. So you can see that both ettringites are formed in these two cases, but the normal setting occurs within, let's say, 2 hours, because a large amount of ettringite is getting formed, which is taking the pore structure, which is consuming the pore structure, and therefore the setting occurs a little faster. So normal setting but faster. Case 3 leads us to what we know as quick set. When the C3 availability or the reactivity is high, while there is still sulfate in the system, but it is low in low quantities. If the quantity of sulfate is low and the availability of C3 is high, then it will form a quick set. Quick set meaning that since the some of the aluminate will form ettringite with sulfate, but with time, uh, this sulfate, when the sulfate gets reduced, it will form hydrogarnets and monosulfate products as well. So that will lead to a quick set. The case 4 is that of a flash set, when the C3A content is high while the sulfate content is almost nil or very low amount. So high and none. No sulfate is available. So what occurs is the C3A forms this calcium aluminate hydrates, and this is also known as hydrogarnets. These are crystalline structures and they set the system very quickly, so it is known as flash set. And this setting behavior is irreversible in sorry, this setting behavior is irreversible in nature, meaning that the cement or the concrete sets for forever, right? And the final case is that of a false set. What happens in false set? When the C3A content is low but there is enough sulfate available, so there is too high amount of sulfate available in the system, what happens is these sulfates combine with the calcium coming from the different clinker phases and uh, precipitate gypsum, and this gypsum leads to a false set. This false set is however reversible, meaning that if you rapidly mix the cement again, then it will not set, and you can carry out the testing of the setting time. So it will first show a false set, so meaning it will be looking like the cement is set, but if you continuously mix it for some time, then the precipitation of this gypsum and the network will be broken, and therefore you will be able to work with the cement and concrete. So this is called as false set, right? This last case false set. So this is the difference between the different types of setting phenomena that occurs in cement. Moving on to the ninth question, this is probably the last question of the session. Which kind of aggregates are the best suited for concrete, rounded or angular, and why? You might have seen, and we have also discussed this in the lectures as well. Rounded aggregates are formed from natural phenomena, like due to the weathering, and when it gets ground, the sharp edges of these aggregates get rubbed against different particles in the nature, and therefore they get smoothened and rounded in shape. Whereas crushed aggregates are generally angular because they are crushed in a crusher, jaw crusher. Which of these type of aggregates are best suited for concrete and why?
Angular aggregate.
Angular aggregate is better for concrete. Why?
Yes, sir. voids को पूरी तरह से फुलफिल कर देता है.
वॉइड्स को फुलफिल कर देता है, राउंड एग्रीगेट्स फुलफिल
नहीं
नहीं कर पाता.
सर, angular aggregate is better as compared to round aggregate because it interlocking the effect in concrete.
Interlocking effect, right? Beautiful, thank you. Yes. So rounded aggregates, as I mentioned, they come from the natural aggregates or pebbles, weathered to smooth texture and rounded edges by natural forces. Right. On the other hand, angular aggregates come from crushed aggregates in a jaw crusher. So boulders are fed into this jaw crushers, and that jaw crusher crushes them into different sizes of the crushed aggregates. Now, there is no direct answer to this question, which kind of aggregates are best suited for concrete, because we know that when the aggregates are angular, meaning if the angularity of aggregates increases, this decreases the packing of the packing density and therefore void ratio increases, right? So when the angularity of the aggregates increases, this decreases the, because round aggregates have the best packing density. When angularity of this, what you're trying to say is, I mean, the packing is improved is when you use different, in order to increase the packing of the aggregates, you have to use different sizes of aggregates. So it has to be a well graded material, so that the lower sized particles take the voids while the higher sized particles maintain the shape. On the other hand, if we are talking about the same size of the aggregates, then angularity of the aggregates increases the void ratio, it decreases the packing density, whereas the rounded aggregates of the same size provide the best packing, right? But on the other hand, if we talk about bond strength between of concrete between aggregates and cement paste, we know that angular aggregates provide better interlocking due to the rough edges increases bond strength. This in turn increases the bond strength. On the other hand, in case of round aggregates, the bond strength is compromised, as the round aggregates don't provide for a good interlocking between the aggregates, and the bond strength is therefore reduced in the case of rounded aggregates. So, in order to decide which is best suited for concrete, you have to find a good compromise between the angularity of aggregates in terms of increasing the packing density, or between the bond strength of concrete. I mean, that you require for the for your concrete mix. Now, there is one fix to the to increase the packing density, as I mentioned. It is to introduce different sizes of particles to use a well graded aggregates, so that you have a better packing also, and you also take the advantage of interlocking between the angular aggregates. On the other hand, if you want to have uh, a higher bond strength when you use rounded aggregate concrete, you have to mix it with certain angular aggregates, or else you'll have to use those kind of aggregates which have a rough texture. Rough texture aggregates also allow for better bonding. The smooth texture of aggregates do not, I mean, compromises the bond strength of the between of the concrete. So this answers the last question. Thank you. If you have any questions, that ends the today's session. We have still around 20 minutes left for the session. It will go on till 8 p.m. If you have any doubts regarding this session or the practice questions that we just discussed, or any doubts regarding the week 2 lectures that you might have watched, then we can discuss them now. If you don't have any doubts or questions or queries, then you're free to leave. The session will go on till 8 p.m. All right, we are closing the session for today. We'll meet again on next Monday from 6 to 8 p.m. Thank you.